Here is a combined summary of the 2 pages. This paper presents a novel method for safely navigating a fixed-wing unmanned aerial vehicle, UAV, along a desired route while avoiding moving obstacles. The proposed approach utilizes a class of control barrier functions, CBFs, based on collision cones to ensure that the relative velocity between the aircraft and obstacles consistently avoids vectors that might lead to a collision. The CBF is demonstrated to be a valid constraint for the aircraft, enabling its real-time implementation via quadratic programs, QPs, termed CBF-QPs. The paper begins by introducing the challenges of safe operation in increasingly cluttered environments, highlighting the need for effective collision avoidance techniques. It then presents a brief overview of runtime assurance (RTA) systems, which have been developed as supplementary modules for aircraft flight controllers to prevent safety violations. The kinematics of fixed-wing UAVs are described, followed by a formal introduction to control barrier functions, CBFs, and their importance in providing formal safety guarantees in safety-critical applications. The collision cone control barrier function, C3BF, approach is introduced, which combines the idea of potential unsafe directions given by collision cones as an unsafe set to formulate a CBF. The CBF candidate is defined as a function of the relative position vector between the body center of the aircraft and the center of the obstacle, the relative velocity, and the half angle of the cone. It is shown that this candidate is a valid CBF for fixed-wing UAVs, and its application is demonstrated through simulation results. The paper also discusses the quadratic programming (QP) formulation of CBFs, which acts as a safety filter that takes the desired input and modifies it in a minimal way to ensure safety. The explicit form of the CBF-QP control law is obtained by solving the optimization problem using KKT conditions. Finally, the paper outlines the organization of the rest of the paper, which includes the application of the CBFs on fixed-wing aircraft to avoid obstacles modeled as spheres, simulation setup, and comparative results. The paper proposes a novel approach to collision avoidance for fixed-wing unmanned aerial vehicles, UAVs, using control barrier functions, CBFs. The authors introduce 2 CBF candidates, a naive CBF and a CBF with backstepping. The naive CBF, defined by equation 9, is valid only for a specific set C, while the CBF with backstepping, defined by equation 15, is valid for an extended set D. The relative position and velocity vectors between the aircraft and the obstacle are computed using equations 11 and 12. The VREL term, which contains the inputs AT, P, Q, is calculated using equation 13. The authors prove that the naive CBF candidate is a valid CBF defined for the set C in Theorem 1. However, this CBF has limitations, as it can only alter the aircraft's pitch and longitudinal acceleration, making it uncontrollable by the safety filter. To address this limitation, the authors propose a CBF with backstepping, which extends the safety set from C to D. The new CBF candidate, defined by equation 15, includes the desired roll rate RDs and uses backstepping to determine the roll rate R. The authors prove that this CBF candidate is a valid CBF defined for the set D in Theorem 2. The authors validate the proposed CBFs using Python simulations and compare the results with an existing CBF. The simulations show that the proposed CBFs produce a smoother path with minimal deviation from the trajectory while ensuring safety. The authors also note that the CBF with backstepping can handle obstacles that cannot be flown over, whereas the naive CBF can only make the aircraft stop. The paper concludes by highlighting the limitations of the current work and proposing future research directions, including comparing the results of the naive CBF with the CBF with backstepping for cases that set them apart and extending the analysis to collision avoidance with lawn obstacles.